You have probably heard the term something growing exponentially. And I think sometimes it's just used for something growing very fast. Well, in this video I'll talk about the actual mathematical model, which we would consider to be an exponential growth. So here's the basic formula, whether you're going to grow or decay. Now, it can occur in other forms, but for this video I'll look at it this way. And this A could be any letter, depending on what it is you're measuring. Here I just did a generic A for amount of something. But if you're looking at population, you might be writing P for population. You could use your own letter. The sub-zero refers to at time zero. So actually this A sub 0 will be a number, always. It's not a variable in its own right. And the R is at what rate it is growing or decaying. So if it's growing by 50% per year, R would be 0.5. Now R is always a decimal. Any percentages you convert to a decimal. And if it's decaying by 25% per year, R would be a negative 0.25. So decays are negative, growths are positive. And T is time measured in whatever the R is measured in. So if this is growth per year, T would be measured in years. If this is growth per hour or decay per hour, T would also be measured in hours. Okay, so let's look at some examples and how to solve. So first, how to solve for the A. So I've got this story problem here. A town has 100,000 residents. It's growing at 3% per year. And then if it continues growth at the same rate, meaning if we can use an exponential growth model, because every year it grows by 3%, then how many residents will it have in 10 years? All right, so in the formula I had before, A sub 0, remember, was the amount at time 0. So we're going to just declare that the 100,000 is times 0, and thus A0 is 100,000. And they said 3%, but we write it in decimals, so we write it as 0.03. And then we put those two into the main formula, and we get A is 100,000. 1 plus 0.03 to the T. Now, as I mentioned, you could use your own variable. P for population would work just fine. R for residents, number of residents, would work just fine. Now, in this problem, the question says it gives you time. And notice this was 3% per year, and time is in years. So, okay. All we will have to do is plug in T is 10. And there's nothing fancy here. You're just going to use your calculator to work that out. Or if you really wanted to, you could multiply 1.03 times itself 10 times and multiply the result by 100,000. But the calculator is much faster. So, okay. So you just, this is what is called a plug and chug problem. You just plug the numbers in and chug it out on your calculator. Boom, there it is. There's the answer. Okay. This is the easy problem. The harder problem is when you solve for time. Okay, so here we have an example solving for time. Same thing, same town. Okay. But now, if it continues to grow at the same rate, how long until the population doubles? And in exponential growth, we do have this doubling time type of question that comes up often. Okay. So, all right. So here was our basic model as per the previous, as what I did previously. And so if you're asking the population double, so the new population will be 200,000. Looks like I have an extra 0 there. Let me remove that. Okay. So the new population will be 200,000. And then you put that in for A. So 200,000 is 100,000. Times 1.03 T. And to solve these, to solve for the time, I need to get rid of this. So I'm dividing both sides by 100,000. So dividing this side by 100,000 gives me 2. Dividing this side by 100,000, they cancel out. And I'm just left with a 1.03 to the t. And then in trying to solve for the exponent, we have this tool called logarithms. I'll take logarithm of both sides. So logarithm of the left side, logarithm 2, is logarithm of the right side, 1.03 to the power t. Now, and here's the special thing about logarithm. This is why we want to use it. Is that if you have a logarithm, and inside of the logarithm here, inside of the logarithm, is a power, that power moves out front. That is a special property about logarithms. So that t can be written out front. And now it's just t times logarithm 1.03. So I can easily solve for t, since this is t times, I'll divide. So I divide by the logarithm 1.03. And this is calculator work. And so it comes out to be, roughly 23.4 years. The population will double. So it will take a while. Okay, now in decay, I mentioned earlier, the R is negative. So I'm doing what is called a half-life problem. I've told you that this isotope francium-223 decays, 3.10% of it decays every minute. So time is now measured in minutes. And if we start with 2 milligrams of the material, how long until you only have half of it because it's breaking down? So here's my basic model. My A is my beginning amount, 1 plus the decay rate, which is now negative, and converted to a decimal, to the power t. And then I just simplified this. 1 plus that negative number came out to be 0.969. And I also plugged in A as 1. Why 1? Because I'm supposed to have half. So I went from 2 to a 1. Okay, and then like the previous problem, I'm going to divide both sides by this thing here, right there. And that gives me a half. That is 0.969 t. I take logarithm to both sides. I've skipped a step. I've moved the t down. Okay, so I took log of 1/2 equals log of this thing, and then I moved the t down in front. And then I just divide both sides by this log 0.969. Okay, and so the answer is 22 minutes. Okay, and now something outside math just to tell you. So this word isotope. So I'm certain you've heard of elements. We have, the element of carbon, the oxygen, hydrogen. You've heard all these words. If in addition, a chemist or physicist talks about the combined number of neutrons and protons, and that's what this 223 is, it's part of the name. It's telling you that in the nucleus there are 223 neutrons and protons stuck in that nucleus. Then we have an isotope. So for instance, with carbon, the most common carbon is carbon-12. And so when people talk about carbon, they're probably talking about carbon-12 or something that might be mixed but is mostly carbon-12. And then you also hear about carbon-14 dating. So that's carbon with an extra 2 things in its nucleus. Those are called isotopes, right? So they're both carbon, they're both the element carbon, but then one has 12 things in its nucleus and the other one has 14. And when you get to that, you call them isotopes. Anyways, this francium is naturally occurring but very rare, because look how quickly it disintegrates. It actually is formed when an even larger isotope breaks down, and it breaks down into this, into francium, which itself quickly breaks down. In 22 minutes, half of it is gone. They estimate that there is less than an ounce of this on the Earth, and naturally occurring. Now you can make it in the laboratory, but naturally occurring at any one time, there's only an ounce. That's it in the entire Earth, because it decays so quickly. All right. Thank you for listening.